All right, everyone, it is my pleasure to introduce somebody who really needs no introduction. Our own esteemed Bill Eberhard from the Smithsonian Tropical Research Institute presents to us possible self-assembly in linyphiid sheets. Bill?
Okay, thank you. This talk has a very simple structure to it. I'm first going to set up a puzzle that I ran across looking at the sheet webs of a pair of species of linyphiids. Then I'm going to describe a hypothesis that I invented to try and explain those observations, a test of that hypothesis, and then try and think about the implications of what I've found. So I started with a pair of species of linyphiids. As we all know, Linyphiidae is a huge family, one of the biggest of all spider families. Generally, they make sheets of silk, sometimes with tangles above or below that are larger or smaller. These are the two species that I looked at. And basically what I did was bring them into captivity, get them to build webs in rectangular frames made of wood and wire. This is a frame of web of Linyphiid simplicata, seen from the side at the upper left, then from above the sheet and a close-up of the sheet. And basically I looked at them with two techniques. First, I used a dissecting scope, and what I found was, when I looked at it under the dissecting scope, that the sheet was composed almost exclusively of threads that were bearing droplets. And you can, when it's in good focus, you can see the droplets along a given line. All of the dark lines in the photo on the left are carrying droplets. There are a few lines that you can just barely see, and those are lines that don't have droplets. So the first thing that I found out was that nearly all the lines in the sheets have droplets on them. Then I looked at the sheets under a compound scope, and sure enough, the droplets are even more obvious, and almost all the lines bear droplets. Droplet-bearing lines lack at their intersections. They don't have piriform attachments. The one line goes past the other, usually with a larger droplet, or apparently larger droplet at the intersection. And in very few cases, there were what looked like piriform attachments at the lower right, and those were all between lines that didn't bear droplets. So I wondered whether the general impression that the droplets were larger at the intersections was true. So I set out to measure, and I measured the droplets at the intersection, the spaces around those droplets, all that's in red, and then used as control the adjacent droplets and the spaces between them. So, and what I found was that the droplet diameters, as I thought, were much larger at the intersections than they were at the controls in both of the species. So that I found intersection droplets are larger, and I also found that the spaces around those intersection droplets are larger. Then I looked a little bit at the behavior, and what I saw was basically identical to what Benjamin and Schock had found with another species in Europe, that the spider wandered back and forth while building the sheet, wandered back and forth across the sheet. And as it did so, it periodically dabbed, as in the diagram on the right, dabbed its abdomen upward, apparently against the sheet. It never dragged the spinnerets across the sheet, but rather only occasionally touched the sheet with these dabbing movements. And when it made the dabbing movements, no legs near the spinnerets were holding lines. So it didn't look like piriform attachments were being made, and that fits, of course, with the observation that there weren't any piriform attachments between lines bearing droplets. These trips were long and relatively rapid. Benjamin and Schock measured the distance traveled in 12 minutes. The spider traveled something like 8.5 meters. Then I did a couple of very simple experiments. First experiment really was designed to test the question of whether or not the droplets are actually sticky. There's been controversy in the literature over whether or not they are. And what I did was on the left, take an insect pin, a clean, shiny, smooth insect pin, touch it to a line, and then pull it away to see whether the line stuck to the pin. And sure enough, it usually stuck to the pin, usually stuck until the line was displaced more or less as in that drawing, and then popped off. So what I found was that the lines with droplets were weakly sticky. When I did the same experiment with lines without droplets, they never stuck at all. Then I did one further simple experiment with the pin. I put it on a line in the drawing B, it would be line B, and then pushed that line more or less parallel to the other line near an intersection and watched what happened. What I found was that when I did this, the lines almost always adhered to each other. And when they did adhere to each other, often they broke apart. They snapped apart. And then if I pulled the pin away, I found that the two lines were not in the same plane. One was above the other. And in no case did the slippage that I was looking for ever occur. So you see that when they cross, they're almost always attached, and when they come apart, then they're not in the same plane. So here's the puzzle. We've got these lines bearing droplets that are sticky. They often adhere to each other despite being in different planes. The droplets in the spaces are larger at the intersections than they are on other parts of the line. But the behavior of the spider shows that there's no way that the spider is modulating the application of liquid to the line to produce these larger droplets and these larger spaces around the intersections. So how can we explain these droplets and the spaces at the intersections? And I invented the hypothesis, which I'm calling the self-assembly hypothesis. And that is that perhaps the larger droplets and spaces are due to the lines scraping against each other. And as when they scrape against each other, they move the glue along the line. And that these movements actually of the lines themselves are actually a result of the dabbing behavior, which both Benjamin and Joke and I at first had thought must be production of piriform attachments. Surely they're not a production of piriform attachments, but perhaps they're pushing the lines with this dabbing behavior, and perhaps they're also stressing the lines and moving them when they walk under the web. And I suppose perhaps that the larger droplets at the intersections are advantageous because they increase the ability of the sheet to resist stresses from prey and perhaps also adhere more effectively to prey. How could one test this hypothesis? Well, there's one very simple and obvious prediction. It should be that the intersections that have especially large droplets also have especially large spaces around them. Those would be intersections, according to the hypothesis, where the lines have moved more, scraped more one against the other for a longer distance and accumulated more glue at the intersection. So I measured the relative diameters of droplets, correcting for the diameters of droplets in the control droplets around the intersection, measured the spaces, again, correcting for the mean spaces around the intersection. And lo and behold, there was indeed the correlation that the hypothesis predicted, that relatively larger droplets had relatively larger spaces around them. So this, the consequences of this are interesting because the simple idea of linyphiid sheets needs to be modified and rethought a little bit. It appears to me that what happens is the spider has an adhesive, and it has the problem of distributing this adhesive in its web. And what it does is relatively uniformly applies the adhesive to many lines in the sheet, but then uses subsequent movements of these lines, some of which it produced itself, and others perhaps that occur when it walks, and also perhaps occur when a prey strikes the web. And these movements of the lines cause accumulation of glue at the intersections and thereby increase the sheet's ability to capture prey. So with that, I'll just give my thanks to people who identified the spiders for me, Tiago da Silva Moriera and Gustavo Hormiga, and thank for financial and logistic support, Smithsonian Tropical Research Institute and the Universidad de Costa Rica. Thank you.
Bill, thank you so much. We have just under about around 4.5 minutes for questions. So let's see, we've got a question from John Coddington. Is absence of piriform connections at SS line junctions a derived character for linyphiids?
I'm sorry, I didn't understand the question.
Is the absence of piriform connections at the SS, is the abbreviation, line junctions, a derived character for linyphiids?
Well, I don't think there's enough known about in other groups to answer the question yet. It's basically, as far as I know, people had not realized that it's actually relatively old news that there are sticky lines in linyphiid webs, and the person who best demonstrated that in the past was Frank Millage, a taxonomist who looked at a number of different linyphiid genera and found exactly what I found, that most of the lines were droplets, and the droplet bearing lines were adhesive. But the rest of the intersections between the lines, nobody really has looked at, as far as I know.
Yeah, but Bill, the intersection between SS lines and almost anything, right, usually non-sticky lines, is almost always elsewhere with a piriform junction. So that's interesting. I agree that we don't know a lot about linyphiid diversity, but big news that they don't have piriform junctions.
No, well, that's not the news I'm giving. They do have piriform junctions, but they're strictly between the lines that don't bear droplets.
Yeah, non-sticky lines.
Non-sticky lines, and so what they've done, if assuming they're derived from orb weavers, they've abandoned the attachments of sticky lines to other lines and simply allowed the sticky material on the line to make the binding. But the piriform attachments are still clear and easily recognizable, but they're only on the non-sticky lines.
Yeah, I mean, it means that linyphiids almost uniquely within araneoids sticky lines without piriform junctions. And nobody else that I know in araneoid sticks sticky lines to sticky lines with piriform junctions. So I don't know, they're weird. That's great.
And on
right,
that point,
and I presume, although I didn't look carefully at the junctions, I suppose that the sticky lines that cross non-sticky lines also have the same also have the same droplets of glue that accumulate there.
Yeah, I don't want to bogart the question session, so ask some others.
Yeah.
Bill, if you could please unshare your screen, that would be useful.
Okay, I'll try.
So on the point about linyphiids being weird, Martin Ramirez asks, are linyphiids hanging from sticky lines all the time?
Again, I'm sorry, I didn't understand the question.
Martin Ramirez asks, are linyphiids hanging from sticky lines all the time then?
Most of the time anyway. I suspect that the sequence, as far as the Benjamin and Jock found, the sequence of building a web is first make non-sticky lines and then fill in with sticky lines. So I suppose that they are walking under both of those types of lines at one time or another.
All right. And then
The question, a good, interesting question that I have nothing to contribute on is whether how the spiders avoid sticking to their own sticky lines. But in fact, the stickiness is very weak. So I suspect that may not be a problem.